Okay, so before we start running through the mechanism, let's look at the reaction and see what it is we can get from the reagents, the solvent, temperature, and that sort of thing. So let's get as many clues as we can first from looking at the reaction, and then we'll jump in and start working on the mechanism. So if you look at the reaction, a couple things that stand out right away are, number one, we have here a polar protic solvent, methanol. That means we can solvate intermediates in this reaction that are going to be highly polarized, or maybe even carbocations. Because remember, if you have carbocations in a mechanism, you better have methanol, ethanol, or water as a solvent. Otherwise, you will not be able to make those as intermediates. But that's not going to be a problem here because we've got methanol, so we can even form carbocations in our mechanism. Then over the arrow, we have some acid and some heat. And so because of the acid, that's where I would say, okay, so then just remember that I'm going to say the pH is going to be acidic for this mechanism. If the pH is acidic, I will draw a circle somewhere on my quiz and fill it in with a plus sign, so that as I go through the mechanism, I make sure that I don't draw any minus signs on any substrate along the way on the in the mechanism. Because every time you draw a negative on it, like an alkoxide or a carbon with a minus charge, it's going to be wrong. You know it's going to be wrong because you've got a plus in this circle right here. So you cannot have anything but pluses on the intermediates in your mechanism. So that's pretty much all you can get from the reagents and what's over the arrow. The question as to the radio label and where does the radio label show up in the products? Is it A? Is it B? Is it both? That's actually a question, we'll not worry about that right now. We'll get to that at the end when we actually figure out what the best mechanism is, and then we can go back and look at it and say, okay, so let me be that radio label. Let me follow through the mechanism to see, is it going to be an A, B, or both? So we'll worry about that question at the very, very end. Okay? All right, so then let's run through this. Let me give you a new page here to have space to write on. So, okay, so here we go. So the first thing we do is, of course, we are going to protonate. And we protonate best nucleophile, goes after best electrophile. Don't forget you have two lone pairs on this oxygen here. So one of the lone pairs is going to be the nucleophile, and it's going to go after the H+. And so after that, you'll get to this. And what this is going to do is it is going to have a resonance contributor where what you're going to do is you're going to put some positive charge on this carbonyl carbon right here. And so what you're doing here is you're activating this molecule really to give the carbonyl carbon some plus charge right there. So we'll go ahead and look at that resonance contributor. So that's going to be a double-headed resonance arrow here, right? And then that will give us, oops, a little bit sloppy there. And then that will give us okay, so the other resonance form here, you've got the plus charge on the oxygen or on the carbon, or on the oxygen to carbon, back and forth in between these two resonance contributors. And then you notice when you do have the plus charge on the carbonyl carbon, that's actually where you're going to actually do your chemistry for this reaction. If you play Where's Waldo with the starting material on the product, you can see it's going to be at that central carbon where you're actually changing something, where you're actually swapping out a OH and putting in place of it a O-methyl for the methanol. So here's where we add our methanol in. So we're going to have our best nucleophile, which is going to be the lone pair electrons on the oxygen. So best nucleophile there goes to our best electrophile. That's going to add in, and we're going to get to here. There you go. And a plus charge here. And every time we make charge, we hate charge, get rid of charge. So let's just deal with that first. And so let's just take any solvent molecule, or I'll just do the general base symbol. And I'm going to pull off the acidic proton, which has pKa now like -2 because it's got an oxonium ion, right? So it's going to leave lone pair of electrons behind on the oxygen to give it a lone pair. Okay, so before we do the mechanism, let's do a quick inspection of the reaction and see are there any hints or clues we can get by looking at the structure of the product, the structure of the starting material, maybe the solvent you're using, the temperature you're using, the reagents you're using. And so if we do a quick inspection of the reaction, we say, okay, so what do we got going on here? We have carboxylic acid, and we have methanol, which is also probably acting as our solvent. Then we're going to use a catalytic acid to get this thing to go, and then we have heat as our only reagent here to get the reaction to go. So if I play Where's Waldo on the starting material on the product, when I say, well, it's right here at this carbon, that's where something's going on, because here I've got a carbonyl and an OH, And then that same carbon in the product, I've got a carbonyl and an O-methyl, so I want to focus on this carbon when I do my play Where's Waldo, because that's where the chemistry is taking place, right? The fact that I have methanol is key, because then I know that I can form carbocations in the mechanism. Remember, methanol, ethanol, water, the only solvents you'll see that will be used for doing SN1 type mechanisms where you can form carbocations. Without the methanol, or ethanol or water, you cannot form carbocations. So because of methanol, it's going to be okay to form carbocations in this reaction. That's cool. And then finally, we have H plus as the acid to get this thing going. So this is acid catalyzed. That's when I say I'm going to put a circle on the far right-hand side of the page, and I'm going to fill that circle with a plus. And so as I go through the mechanism, I'm going to say, okay, I'm going to make sure that every substrate, every intermediate, every reactive intermediate along the way in this mechanism, whether it's going to be 5 steps or 25 steps, everything's going to have a neutral charge, no charge, or it's going to have a plus charge. I don't want to see anything with a minus charge on the substrate, because now that I see this plus in the circle, that's your math accounting little trick there, where you're going to make sure, do not violate this. Do not draw any minus charges on any of your substrates in the mechanism. So if you have all of that, I think that's pretty much all the clues we're going to get from looking at the reaction and what's over the arrow. And so this question here about what's going on with the radio label and where does it show up in the product, well, that's something you shouldn't worry about until the very end, because first you want to make sure you have the really good understanding of how the mechanism works. Then you'll be able to go back and look at it and say, oh, okay, so if this is the mechanism, then I think I understand what's going to happen with the fate of the radio label on the oxygen there. So we won't worry about that until the very end, okay? All right, so let's take a look at how we're going to do this. So first we got the carboxylic acid, and we're going to start off with acid catalyst. So I'll draw a proton here. And we're going to protonate the oxygen with its lone pair of electrons. Best nucleophile goes after best electrophile, as is always the case, right? And so from there we get to here. And then from here, we can see we have a plus charge now on this oxygen. And I also have a resonance contributor. So I'm going to go ahead and draw that resonance form, where I'm going to take the electrons here, and I'm going to move them towards the positive charge, because that's what electrons do, right? And then that will show me how we have got this contributor here. And what I see here is plus charge of the carbon. So remember, these two things are the same molecule, right? We're just looking at them in two different forms. This is the form I prefer to look at, because, of course, that's where I remember I said that's where the chemistry occurs. That's what you want to focus on. So that's how we're going to get the other oxygen added in here to introduce the methanol into the product. So I'll take my methanol with its lone pairs of electrons, and I'll have those be nucleophilic, so the nucleophile goes after the electrophile, and that'll get me to here. And I have a plus charge there, so I got the oxygen ion. So that means the pK of this proton here has now dropped down to like -2, so very, very acidic, so it's going to be easy to take off. I will use the general base symbol to show you how you're going to get it off. In this reaction, the general base will be methanol, but if you want to draw methanol, fine, but if you draw something else other than methanol, you might lose points for drawing the wrong general base. So with the general base here, I'm going to then use that to take off the proton, leaving a pair of electrons behind on the oxygen to give it its full octet, and then I get to here. And so when I look at this, I say, okay, so what is this? Well, a couple of ways to look at it, a couple of things you can call it. You can say, if I want to look at how do I look at these two oxygens here bonded to the same carbon? Well, that's a hemiacetal, and I know a lot about hemiacetal chemistry from that chapter we did a lot of hemiacetal reactions on. If I look at these two oxygens here, then that's actually a 1,1 gem diol, or a hydrate of a carbonyl, and we did a little bit of that. So that's to me, that's really just a carbonyl. So that can help you think about, like a Starburst type diagram. Like, think about everything you are, everything you could become, everything you came from, possibly, as a way to kind of pull this together. You can do that for a synthesis problem, or here for a mechanism problem. So here, what are we going to do next? Well, by the way, one more final thing. So the other way you could describe this is you could describe this as a, and I'm sure some of you already are saying the word in your heads, it's the Myron-Bender intermediate, where you've got this central carbon, you got these 3 oxygens around it, and the thing's going to collapse, and when it collapses, it's going to result in a more stable product. And so we remember, if you think back to where you were going with this, you're making the methyl ester of the original starting carboxylic acid. So you make the methyl ester. right now you've got no double bonds here. So when you do install a double bond, it'll be not a change in oxidation state when you do that, but it will be a better, more stable molecule because, for instance, if you were to take this carbon here and say it's bonded to an oxygen and it's bonded to an oxygen with 2 sigma bonds, and then take that and make one pi bond where you've got a double bond, well, that's going to be a shorter, stronger, tighter bond with the double bond. So that's a good trade-off for the molecule energetically. So what I'm going to do here is I'm going to say, okay, so I'm going to protonate either this oxygen or this one. Which one should I protonate? Who cares, right? There's a symmetrical molecule. It doesn't matter which one you want to protonate because it's going to happen 50-50 anyway. And so just pick either one of them, and then we'll go ahead and add a proton. And with a proton, we have the best nucleophile. Goes after the best electrophile. And that gets me to here. So we protonate alcohols because OHs are crappy leaving groups. Now we're going to make this a much better leaving group because as the oxonium ion is going to break away, we're actually losing H2O, neutral water molecule here, right? So we're going to take these electrons, go this way. We're going to be losing H2O there. And so we end up with, so minus water, and we end up with this. With a cation here, nice tri-substituted, resin stabilized, actually doubly resin stabilized, so it's an awesome cation. Then the next thing that's going to happen is going to be, so remember we usually say that, or I usually tell you that, if you can, do mechanisms stepwise, only do concerted when and if you have to. If you can avoid doing concerted, do it stepwise. So another kind of rule of thumb there is if given the option of going to an intramolecular or an intermolecular step in a reaction or in a mechanism, always choose the intramolecular because it's going to be faster, sometimes like 30,000 times faster, to go for the intramolecular step rather than intermolecular. So when I see this plus charge right here on the intermediate, and I see a intramolecular way to deal with getting rid of that charge, then I'm going to go with that direction. So all charge is bad. We hate charge. Do anything you can to get rid of charge. And so I'm going to say I'm going to take one of the lone pairs of electrons on the oxygen, and I'm going to have them resonate down, and that's going to now spread out the plus charge across 2 different atoms, and so it's going to make it more palatable. So from here, we make this as our molecule. And this oxonium ion has a proton on it with a pKa of -2-ish, right? So very, very acidic, so even a weak and crappy base is going to be able to pull it off. And so in this case, it gets to be probably methanol, but again, I'll use the general base symbol. And so I'll say my final arrows I'm going to be looking for to count are going to be take the base, pull off a proton, have the proton give the oxygen its lone pair of electrons back, right? Don't just throw the arrows going off into space someplace, right? Show exactly where they start and exactly where they finish. That's all you need to do because you're saying, I'm showing you where the electrons start and where the electrons finish, and that's what you need to do for the mechanism. So that is the full, complete mechanism because, of course, after that last step there, what do we get? Well, we get this. And so this is the methyl ester of acetic acid. So it's called methyl acetate for the ester nomenclature. So methyl acetate. Okay, so if that's the complete mechanism, then the question is, from the previous page, the question is, right down here. So the question is then, okay, so if I'm going to use a radiolabel on this oxygen here, and I run the reaction, what is the fate of the radiolabel? Does it end up in A? Does it end up in B? And I think it's pretty easy to say it's going to end up in A because you've got the carbonyl with a radiolabel on it, and so it looks to me like maybe that's the same carbonyl right there. And if it is, then it should be radiolabeled. But if you go through the mechanism, you look at this, you're going to say, wait a minute, actually, if I put the radiolabel here, the mechanism is going to get scrambled because at a given point, and it's the Myron-Bender point in the intermediate for the molecule here, so we look at this piece right here. Remember, we said, do you want to protonate this oxygen or do you want to protonate this one? It doesn't really matter. You can do either one. And will one work better than the other? No. What I say is this is where you lose your institutional memory of where you came from as a radiolabel, right? So because of the symmetry running through this here, where these are the Gemini twin diols, then you could protonate either one falls off, and when either one falls off, that means you don't know anymore. Did this oxygen come from the carbonyl, or did it come from the original OH of the carboxylic acid? And then vice versa for this one down here. So when you lose all institutional memory of where did that oxygen come from, then you lose the memory of what the radio label started out on. And therefore, when we went over this in class, I told you that we could do this in one afternoon in the lab, where I can split the class into 3 pieces, have one group perform this experiment where you're going to radio label this oxygen, have one group radio label this oxygen, and have the third group radio label this oxygen, and then you look at the data you get from that, and groups 1 and 2 are going to get a 50-50 mixture of radioactivity in their aqueous and organic layer when they work it up. Only group 3, where you radio label the alcohol, is going to get the radio label showing up in the aqueous layer. In the organic layer. It's going to be showing up right here in part of the ester, but not in the aqueous layer. There's no way to get into the aqueous layer with the mechanism we're proposing here if the radio label starts out on the alcohol when you do the synthesis. So we went over that in class, and hopefully by now you're pretty comfortable with that, because that's one of the tricks we use all the time when you're trying to say, okay, I got this reaction, it works well, it's really cool, I use it a lot, but I'd really like to understand how it works, because if I understand how it works, then maybe I can actually expand upon it, maybe come up with a couple of variations on it, maybe get my name after it, and maybe figure out how to use it in synthesis of a Lyrica compound or something. So to be able to do a reaction and have it be reproducible is awesome. To be able to do a reaction and have it be reproducible and understand why it's working the way it's working, that's like the ultimate goal for somebody doing synthetic organic chemistry. So for this one here, for the last 2 points on this quiz, you should have circled both A and B for this one for 2 points. Okay. So if you have any questions about this, let me know. Shoot me an email, and I'll be working on grading them, over the week. I'm checking mostly over the weekend if I can. And but at least you got the answer key here. So if you have any questions on this, let me know, and then we will be doing alpha carbon chemistry in class on Wednesday night. All right.